So let's say this is our vector field F, and a vector field is shown in the red arrows. Now if we want to calculate how many vector field lines are passing through this surface S, then how we will calculate this? So let's chop this surface down into the small, infinitesimal small patches, and like this picture. And if you take this small patch and calculate flux or the vector field lines passing through this small area, then let's say this is our small ds, and at this point, let's say the vector field F is given by this, okay, and if we want to calculate how much flux will pass through this small surface ds, that means how much field lines is passing into the direction of this normal n cap, okay. So the direction of the surface is given by this n cap, okay, and we want to calculate how much vector field will be going into the direction of n cap, okay. Now if you take the dot product of this vector f with this normal unit vector, then you will be finding the vector field which is going into the direction of n cap, and if you will simply multiply this expression by ds, then this will give you the flux or the vector field lines passing through this surface ds, okay. Now if you want to calculate the total flux through this surface S, then you need to calculate the flux through all these small surfaces, yes, and then you need to add up all these small fluxes. Now you can integrate in order to calculate the total flux f dot n cap ds over this surface, and this will be our total flux through this surface, and this is what we call surface integral, okay. So we also call it the total flux through this surface S, okay. Now in order to find the total flux, or in order to calculate the surface integral over a surface S, you need to find this expression n cap multiplied by ds, okay. Now I am giving you the results from the mathematics, okay. If you need to find the proof of this result, you need to look at the calculus part, okay. I will not be giving you the proof because this is not the mathematics class, and so let me giving you the result by which you can calculate this normal vector and the ds part. So this is the basic general expression for getting the normal vector n cap and the ds, but you need to get first the surface in terms of the parametrization, okay. So if you are given any surface in the form of parametric u and b, then you can calculate this normal vector n cap h, this expression, and then this small surface ds by this expression, and if you just multiply n cap with ds, then you will be getting this expression, okay. So just note down and remember, and I will be giving you the link from which you can look at the proof of this expression, okay. But this is the direct result once you have the surface in terms of the parametrization, okay. And this du db is the surface area, little surface area dA in the domain, okay. So you can look at the proof for this expression. Now if you have the surface in the form of z is equal to f of xy, then by this expression, by this n cap ds expression, you can calculate this expression for this surface z is equal to f of xy by this, okay, like this. So I am giving you this expression because most of the questions have the surface in the form of z is equal to f of xy, okay. Then you can calculate n cap ds by this expression simply. So this is in the form of the vector components, okay. So this is the x component, this will be our vector Yes, n cap ds will be the vector, and this will be our x component of this vector, and this is simply the partial derivative of this function with respect to x. This is partial derivative of function with respect to y, and the z component is simply the 1, and this is dA, the area in the xy plane. Okay, this is the small area. You can calculate it by using dx dy, or you can say it du db, or whatever the domain area you are representing with. So you can say this is the small area. So this is the basic results about the surface integral. Maybe in the next video I will be giving you the problems